Section: Introduction. In this section, we discuss how scaling up visual text pair data using large, high-quality, and diverse datasets at various training stages is essential for developing grounded knowledge of the visual world. This approach has led to significant advancements in large multimodal models, LMMs, enabling them to perform well in tasks like visual question answering and captioning, which helps transition these models from research to practical use in daily life. However, we recognize that this method has limitations, especially when it comes to handling complex and changing real-world knowledge. For instance, it struggles with long-tail information, such as facts that arise after the model's training period or knowledge restricted by privacy or copyright issues. Consequently, leading LMMs often find it challenging to tackle knowledge-intensive tasks that require up-to-date information. When faced with unfamiliar visual or textual inputs, these models can produce inaccurate responses, undermining their reliability in situations where factual accuracy is crucial. To address these challenges, we propose integrating search capabilities into LMMs, allowing them to access external information. Current methods can be divided into two main types: Retrieval Augmented Generation, RAG, which retrieves external information to assist in generating responses, and Prompt Engineered Agents, which use prompts to guide models in performing web searches. However, we find these approaches to be less than optimal. RAG methods often rely on static knowledge bases, leading to excessive retrieval and high computational costs, while prompt-engineered agents do not effectively learn to interact with search tools. This motivates us to develop methods that teach models to search on demand and interact with search tools effectively, ensuring they can operate in dynamic real-world environments. Recent advancements, such as OpenAI's Series and DeepSeek-R1, have shown that end-to-end reinforcement learning, RL, can enhance the reasoning abilities of large models. OpenAI's deep research suggests that training models through end-to-end RL to engage with search tools can significantly improve their performance on complex tasks requiring iterative reasoning. In the open-source community, initiatives like Deep Researcher, Search-R1, and Research have also explored applying end-to-end RL to enhance models' capabilities in search and retrieval augmented generation. However, most existing work focuses on text-based search, leaving challenges in the multimodal domain, such as creating suitable training data and designing RL frameworks for real-world search, largely unaddressed. In our work, we concentrate on training LMMs to develop three essential search-related skills: when to search, what to search for, and how to reason with search results to answer user queries. We introduce MMSearch-R1, the first end-to-end RL-based solution aimed at enabling LMMs to perform on-demand searches in real-world internet environments. Our contributions include: 1. Dataset construction. We present an automated method for creating a multimodal search VQA dataset by assessing the model's familiarity with the necessary visual and textual knowledge for each question. This allows us to generate a mix of questions that require searching and those that do not, which is vital for training the model's search capabilities. We also include manually annotated test data covering various knowledge categories and difficulty levels for thorough evaluation. 2. Multimodal search tool integration. We develop a real-world search pipeline with two tools: an image search tool that retrieves web page thumbnails and titles related to user-provided images, and a text search tool that allows the model to issue specific queries to gather relevant information. 3. Better performance through wiser search. We show that by using an outcome-based reward with a search penalty, the GRPO algorithm can be applied to LMMs without needing cold start initialization. This encourages models to recognize their knowledge limits and search when necessary, enabling them to learn effective multi-turn search strategies. In knowledge-intensive VQA tasks, our MMSearch-R1 to 7B model not only surpasses RAG-based models of the same size but also competes well with a larger 32B RAG-based model while reducing search calls by over 30%. Finally, we plan to open source our data and training framework to support further research in this area. Section Summary. In this section, we discuss the limitations of current large multimodal models, LMMs, in handling dynamic real-world knowledge and propose MMSearch-R1, an end-to-end reinforcement learning solution that trains LMMs to effectively perform on-demand searches. We outline our approach, which includes constructing a multimodal search VQA dataset, integrating real-world search tools, and demonstrating improved performance in knowledge-intensive tasks while also committing to open source our findings and training framework for further research. Section: Building Iterative Multimodal Search Integrated RL Framework. In this section, we describe our Iterative Multimodal Search Integrated Reinforcement Learning Framework, focusing on Group Relative Policy Optimization, GRPO. We use standard GRPO as our foundational RL algorithm, making adjustments to enable search interactions with the real-world environment during the rollout phase. GRPO, a variant of Proximal Policy Optimization, PPO, estimates the baseline directly from a group of rewards, which simplifies the training process by reducing computational demands. More details about GRPO can be found in the appendix. Next, we highlight the importance of a fully functional search toolkit for tackling information-seeking visual question answering, VQA, tasks. We equip our model with two search tools for accessing real-world internet content. The first tool is an image search powered by SERP-API, which matches the input image to the top 5 visually similar web pages, helping the model identify key visual elements. The second tool is a text search pipeline that includes SERP-API, GINA Reader, and a web page summarizer. The model generates a text query related to the original question, retrieves relevant information, and summarizes it into a concise format. To handle complex information-seeking tasks, our model engages in multiple rounds of interaction with the internet before providing a final answer. We structure the prompt to guide the model in reasoning whenever new information is received, allowing it to choose actions from a predefined set. If the model decides to answer, it formats its response accordingly. This iterative process continues until a final answer is given or the maximum number of turns is reached. To avoid bias from the environment, retrieved content is masked during loss computation. We also emphasize the role of reward modeling in our RL training, which encodes desired behaviors and guides optimization. Our reward consists of two parts: an accuracy score with a search penalty and a format score. The accuracy score evaluates whether the model's final answer matches the ground truth, applying a penalty if search tools were used. The format score checks if the model's responses adhere to a specific structure, rewarding compliance. Finally, we aim to create search-balanced VQA datasets that meet 3 criteria. They should include both search-required and search-free questions, elicit concise and verifiable answers, and cover diverse knowledge categories and difficulty levels. To support our research, we are developing a multimodal search VQA dataset called Factual VQA, FVQA, which combines automated processes and manual annotation for comprehensive training and evaluation. Section Summary. In this section, we present our iterative multimodal search integrated reinforcement learning framework, utilizing Group Relative Policy Optimization, GRPO, to enhance search interactions during training. We also describe our multimodal search tools, which include image and text search capabilities, and outline our reward modeling approach that encourages efficient use of search tools while ensuring adherence to response formatting, ultimately leading to the development of a diverse and effective VQA dataset, Factual VQA. Section: Training Dataset Construction. In this section, we outline our approach to constructing the training dataset. To fulfill our objectives, we gather appropriate training data from various sources through 2 key processes: VQA collection and search balancing. For VQA collection, we created an automated system to gather training data that requires visual knowledge. We began by analyzing the metadata distribution of MetaClip, which includes a wide array of visual concepts sourced from platforms like WordNet and Wikipedia. This metadata has a long-tailed distribution, where common concepts, like car and tree, are at the head, while rarer concepts, such as thylacine and astrolabe, are at the tail. We randomly selected 10,000 visual concepts from both ends of this distribution. For each concept, we conducted a web search to find relevant images and their corresponding web pages. We then used GPT-4o to generate concise and accurate visual question-answer pairs based on these concepts. We also classified the knowledge type for each question, creating a knowledge taxonomy. From this, we balanced our sampling and compiled a final set of 6,000 VQA samples, named FVQA Auto VC, with 5,400 for training and 600 for testing. To enhance our dataset with textual knowledge examples, we drew from the open-source InfoSeek dataset, classifying its questions by knowledge type and mapping them to our taxonomy. After balanced sampling, we gathered 7,000 samples, referred to as FVQA Auto TXT. Additionally, we manually annotated 800 samples, called FVQA Manual Train, where annotators selected a knowledge category, found a relevant image, and created a factual question. In the search balancing phase, we aimed to differentiate between questions that required searches and those that did not. We trained a model, Qwen 2.5-VL Instruct 7B, on the full set of samples from the VQA collection. This model generated multiple rollouts for each question, discarding those that did not yield sufficient training signals. We labeled questions based on whether they required image, text, or mixed searches, and created a balanced training set of 5,000 samples, named FVQA Train, with around 3,400 requiring searches and 1,600 being search-free. For evaluating our model's performance, we constructed a high-quality test set, FVQA test, consisting of 1,800 examples that were manually verified or fully annotated. This test set included samples from FVQA Auto VC, InfoSeek Human Split, and our manual annotation process. In terms of implementation, we built our training framework on Vural and conducted experiments using Qwen 2.5-VL7B Instruct. During training, we sampled 512 examples, with each undergoing multiple rollouts. Each rollout allowed for a maximum of 2 search actions, with specific rules for image and text searches. For benchmarking, we selected several datasets, including FVQA Test and InfoSeek, to assess our model's ability in various VQA tasks. We compared our model against both closed-source and open-source models, using 2 workflows: direct answer and answer under RAG workflow, which involved performing searches to assist in answering questions. Finally, we employed the LLM as judge framework to evaluate the accuracy of our model's responses, tracking the search ratio to assess both answer correctness and search efficiency. We used GPT-4o as the judging model to determine the correctness of the responses based on the original image, question, ground truth answer, and the model's output. Section Summary. In this section, we describe our process for constructing a balanced training dataset for visual question answering, VQA, by collecting samples from various sources, including automated annotation and manual curation, resulting in 5,000 search-balanced training examples. We also detail the creation of a high-quality test set with 1,800 verified examples to evaluate model performance across different VQA tasks. Section: Findings. In this section, we present important findings from our experiments. Each finding is backed by quantitative results and thorough analysis, aiming to enhance our understanding of how MMSearch-R1 works and its effectiveness. We hope these insights will validate our approach and offer useful information to the research community. Finding 1. Our reinforcement learning (RL) training helps models better understand their knowledge limits and perform more effective searches. We found that MMSearch-R1 to 7B outperforms similar RAG-based models by an average of 3% in accuracy while reducing the average search rate by about 33%. This shows that our RL-trained model is not only more accurate but also uses external information more efficiently. It competes well with a much larger model, indicating the advantages of adaptive search behavior over fixed retrieval methods. These results confirm that outcome-based RL fosters smarter, cost-effective search strategies. Finding 2. RL training improves the model's ability to create effective text queries and summarize information. Our RL training equips the model with three main skills: deciding when to search, what to search for, and how to extract useful information from results. We evaluated the model's performance in a fixed search setup, focusing on its ability to generate queries and reason over retrieved content. Our results show that MMSearch-R1 to 7b consistently outperforms the base model in both in-domain and out-of-domain tasks. This indicates that RL not only enhances the decision to search but also improves the generation of relevant queries and the extraction of useful information, benefiting both image and text retrieval. Finding 3. RL enhances the model's use of its internal knowledge. We analyzed responses from datasets InfoSeek and Simple VQA to see how the model's behavior changes after RL training. We observed a clear increase in the proportion of correct answers without needing to search, indicating that the RL-trained model can answer more questions correctly based on its internal knowledge. This suggests that RL helps the model rely on its own knowledge when possible and use external searches only for new or complex queries, leading to more accurate on-demand search behavior. Finding 4. RL shows greater performance improvements and higher data efficiency compared to supervised fine-tuning, SFT. We compared the effectiveness of RL and SFT through controlled experiments. For RL, we used a dataset with 5,000 visual question answering samples. For SFT, we created a larger dataset of 13,200 examples from multiple sources. We trained the model to mimic the reasoning of GPT-4o without relying on tool outputs, ensuring it internalizes the reasoning process. After filtering out incorrect responses, we used 8,000 examples for SFT training. We fine-tuned the base model, Qwen 2.5-VL7b, with both datasets and evaluated their performance. The results show that the RL-trained model consistently outperforms the SFT-trained model across all tasks, even with less training data. Additionally, the RL-trained model aligns better with task requirements, especially in using search tools effectively for information-seeking questions. Section Summary. In this section, we present key empirical findings from our experiments with MMSearch-R1, demonstrating that reinforcement learning, RL, enhances the model's ability to recognize knowledge boundaries, generate effective queries, and utilize internal knowledge, leading to improved accuracy and efficiency in search tasks. Our results indicate that RL outperforms supervised fine-tuning, SFT, in performance and data efficiency, allowing the model to better adapt its search behavior based on task requirements. Section. Finding 5. Training with balanced data and a search penalty in the reward effectively guide the model to perform on-demand search. In this section, we found that training with balanced data and a search penalty effectively guides our model to perform on-demand searches. The training dynamics of the reward and search ratio during reinforcement learning are shown in Figure B. When we removed either the search penalty or data balancing, we observed distinct trade-offs. Although both variations achieved slightly higher rewards, they led to excessive use of the search tool, with search ratios quickly approaching nearly 100%. In contrast, our model, MMSearch-R1, which was trained with both data balancing and a search penalty, achieved similar rewards while keeping a much lower and more stable search ratio. This indicates that our model has learned to use the search tool only when necessary, resulting in more efficient and selective on-demand search behavior.